Greetings, friends and fellow fans of sample return missions from our solar system. This is Ask an Astrobiologist, the show that celebrates the science and celebrates the scientists involved in our quest to understand the nature of life in the cosmos, our origins, evolution, the distribution of life throughout the universe. I'm Dr. Graham Lau, your host, also known online as the Cosmobiologist, and we're brought to you by SaganNet.org and the NASA Astrobiology program. Now, this month's special feature episode is going to be so awesome. I actually feel some nervousness of my own right now just thinking about how cool this is going to be. We're going to talk with some researchers who are involved in the OSIRIS-REx mission team. For those who don't know, OSIRIS-REx is a spacecraft that just recently left the asteroid Bennu with a sample in hand to bring it back to Earth for further study. But before we get to that, I want to introduce our ambassadors of the month, those who've done the work of going online on Twitter and other places to share their love for Ask an Astrobiologist. This month's winners, Joe Landon, Denise, and Anirudh Mohanty, who shared their love for Ask an Astrobiologist on Twitter. Thank you very much to all of you for being big supporters of our show. So thank you everyone for tuning in, and I think we can get this started. I'm going to start off by introducing Dr. Scott Sanford. Dr. Sanford is a member of the astrochemistry laboratory at NASA Ames Research Center, investigator for OSIRIS-REx. Dr. Sanford has also been a co-investigator on JAXA's Hayabusa mission and for NASA's Stardust mission. So Dr. Sanford, welcome to Ask an Astrobiologist, and thank you for joining us.
Well, thanks for having me on. I've been looking forward to this.
Yeah, it's so great. I mean, I'm so excited for the whole group here. Before we introduce the rest of the panel, I kind of wonder if you can just kind of briefly give us a little background on the trajectory of your research in all of these different sample return missions, all these different missions, and what you think kind of the grand scheme is for sample return in the future as well.
Okay, yeah, I've been fortunate to be on a number of sample return missions, starting with the Stardust, which brought back samples of comet dust from Comet Wild 2. And sample return missions are a very special kind of mission. They're difficult because you not only need to get to some object in space, but you have to get back, and that increases the complexity. But the advantage of bringing a sample back is that you can do things that you couldn't do otherwise. I mean, most missions go to an object, they do remote observations as they fly by or perhaps rendezvous, and then you're sort of done. Whereas when you have a sample return mission, you can do all those remote observations, but then you get the sample back and you can study it on the Earth. And at that point, your spacecraft's payload effectively becomes all the analytical devices on the planet Earth. And so you can simply do things that you could never do remotely. And so this is just a tremendous power for sample return missions of all types. And I expect in the future we'll be seeing more of these.
Yeah, absolutely. I remember from my graduate work, I was working with synchrotrons, doing X-ray spectroscopy, and I always thought, like, I can't take a synchrotron to Mars or to an asteroid to do this research.
That's an instrument that's not only bigger than the OSIRIS-REx spacecraft, I think it's probably bigger than the launch pad from which the spacecraft left. So you're never going to fly one of those to an asteroid or a comet, but you can bring the comet or the asteroid back to the synchrotron.
Absolutely, yeah. So we have those samples. We can bring them back and study them here. That's fantastic. Our second panelist to introduce is Dr. Jason Dworkin. Dr. Dworkin is an OSIRIS-REx mission project scientist working from NASA's Goddard Space Flight Center. His work is focused on assessing the organic species available for the origins and early evolution of life, with a focus on understanding extraterrestrial sources of molecules relevant for life. Dr. Dworkin directs the Research Astrobiological Analytical Laboratory at NASA Goddard and has taken scientific leadership roles in NASA sample return and in situ missions. So Dr. Dworkin, welcome to Ask an Astrobiologist.
Thank you. I'm excited to be here today.
I'm wondering, before we introduce our third panelist, if you can give us kind of just a general scheme of what the objectives, what the mission goals have been with OSIRIS-REx, both at Bennu and with sample return.
So OSIRIS-REx is, of course, an acronym. And the acronym in this case, a lot of the mission objectives: origins, to study the origins of the solar system, the origins of life, by looking at this sample. Spectral interpretation, to look at this asteroid spectroscopically and apply what we learned to other asteroids, because there's 1 million asteroids, but not 1 million missions to visit them. resource investigation to understand how to perhaps someday mine asteroids and navigate around such small objects. Security, to understand how to track and potentially deflect asteroids. And Regolith Explorer, to look at this asteroid in fine detail, both on the surface and, of course, in our laboratories.
Yeah, that's so many different parts of this mission that are crucial. And honestly, I didn't actually think that much about the security fact, this idea that we might actually need to track these things and be prepared for them as well, which is like a whole other thing besides just the science of studying Bennu.
Indeed. Bennu is a potentially hazardous object with a 1/2700 chance of hitting the Earth in the late 22nd century, so a long time from now. But the data that we get from this mission will enable future scientists and engineers in 2135, when the asteroid does a close approach with Earth, to make decisions about if we need to deflect it, and if so, how. We'll have this wealth of data on the topography of the asteroid and how it responds to when a spacecraft touches it, and details on the sample chemistry, so we can actually design how to deflect it, and of course apply that to other asteroids as they potentially pose threats.
That's wonderful. Yeah, I just read Roman Krasnarik's book, The Good Ancestor, and that just makes me think a lot about how our NASA missions today are making us good ancestors for future generations by preparing for some of that needed work that they'll have to do. So it's very cool that OSIRIS-REx is involved in that. To introduce our third panelist, we have Dr. Eve Berger joining us. Dr. Berger is a senior research scientist at NASA's Johnson Space Flight Center. Her current research includes exploring the effects of impact processes on the formation and evolution of amino acids, as well as looking at extraterrestrial amino acid abundances in meteorite samples. Dr. Berger is a collaborator with the OSIRIS-REx mission and also a Mars 2020 science team member working with the Sherlock team. So, Dr. Berger, thank you for joining us for Ask an Astrobiologist.
Thanks, Graham. I'm glad to be here.
I think for a first question for you, if I can, so you've had a background. I understand that when you were a graduate student, you were working on some samples from VILT 2. You've had a background kind of using instrumentation to study amino acid abundances in these materials, cometary, asteroidal, and in meteoritics. I'm wondering if you can kind of speak to us about this work that you've done through your career now, advancing to the point of becoming part of the OSIRIS-REx team.
Sure. So early on in my career, during my graduate work, I did mostly electron microscopy work, so using transmission electron microscopy. So that allows us to see crystal structure and identify minerals and the relationships they have to one another, which tell us about how they formed or where they formed or under what conditions they formed. And so I carried on doing that kind of work on VILT2 and also chondritic samples. And then a few years ago, I started working with another organic geochemist at Johnson Space Center, and we were looking at amino acids, kind of continuing on the work that he had started. And so we look at what organic compounds are in meteorites, and what I've done with him in the next step is to sort of look at what happens when those amino acids are delivered to the Earth. How do they go from what we see in the meteorite to, well, the life that we see in each other's eyes as we're looking at the screens today? And so I like to cook, so I sort of use cooking analogies. And so if you've ever been out for a good meal, and at the end someone hands you a dessert that is just fantastic, you could continue eating it for the rest of your life, and you think to yourself, I could make that at home, no problem. There's a little bit of chocolate in there. I'm detecting a note of some ginger and maybe a little bit of cinnamon, but you get home and you realize you don't know exactly what ingredients were used, and you don't know exactly how they were mixed together. Was it pan fried? Was it baked? Was it air chilled? All those kinds of things. And so when we're looking at how do we go from organic materials delivered to the surface of the Earth to life, we need to know both the process and the starting materials. And so I can simulate asteroidal impacts in my lab and see if the energy from that impact is enough to promote polymerization or the joining of two amino acids together to form a peptide. Or is it too much energy and they get destroyed? And that's not the way that things progressed on the early Earth. In general, we don't know the process, but we can get a much better answer on the starting materials from OSIRIS-REx. So this will be the first sample that we have from an asteroid that's completely pristine, no terrestrial contamination at all. So it gives us sort of our starting recipe, which is great for someone who does experimental work, because I know that I'm then more closely approximating what happened on the early Earth.
I love that. And I love the analogy to cooking, since I love to cook myself, and trying to reverse engineer dishes can be very hard. So having some knowledge of your starting ingredients and some of the process is really helpful, right? I really love that. I think that's good for our audience too, especially some of the younger ones who might want to get involved in this research themselves one day, to remember that, how they're framing their thinking about being involved in this kind of work. And also, I have a bunch of meteorites in my own collection, and one of my favorites is Murchison, which has an abundance of amino acids in it. And it's always cool to just share that with other people and tell them, we're learning so much about organic chemistry in the cosmos beyond our own planet by having these materials to study. And so that sample return gives us even better material to study, which is really cool.
Absolutely.
I'd like to transfer over to Scott now. If you wouldn't mind telling us, what is it about asteroid Bennu in particular that makes this asteroid interesting for studying with this mission and for bringing samples home?
Well, actually, I think a number of things make it interesting. Jason, going over the acronym, makes it clear that there's actually different good reasons to study this object. The security one being one. Since the three people you have on this panel are into sample analysis, obviously one of our answers is going to be that we think Bennu will provide samples that will be very interesting to study. And in particular, we believe these samples are likely to contain organic compounds. So in terms of this Ask an Astrobiologist angle, this makes them much more interesting. I would probably still be excited to study samples from an iron asteroid, but not as excited as I'll be to get samples from Bennu, because we fully expect the Bennu samples to show a great deal of complexity in both the minerals and the organics, and that these we ought to be able to tease out a lot of information about the ingredients for the cooking, but also the processes that they've already experienced. Since we think Bennu is similar to carbonaceous chondrites, we have an expectation that the samples we bring back will show parts of the material's history, not just through the life of the asteroid, but back into the original solar nebula from which the asteroid formed. And frankly, we would expect there to be components within the return samples that actually predate the solar system, that were grains that existed in the dense molecular cloud that ultimately started to have a portion collapse and make our solar system. So it gives us insights to a huge range of the prehistory of the materials we'll be returning to Earth.
Absolutely. Yeah. I think a lot of people are unaware of things like pre-solar grains and other materials that do predate our solar system. And when we use this term primitive, we're talking about some of the earliest solid materials to have formed in our solar system.
Yeah, we know from meteorites that we have grains that come from supernova, from nova, from all kinds of dying stars. We have materials that actually form themselves in space in the dense molecular cloud. So we have astrochemistry that isn't even associated with the star. And the kind of detail you can get from this just kind of blows your mind. I think we know on the basis of titanium isotopes in a certain kind of grain that we have materials in the solar system that came from at least 7 different stars. So you can, once you can start picking the atoms apart, and this is one of the advantages of sample return, you can look at things at a level of detail that's just kind of mind-boggling.
Absolutely. That's incredible. I actually hadn't heard that number before. I have to go look into that more. That's really wonderful to know that we're piecing together our solar system's history from these materials as well, the birth of our solar system. Jason, if I can kick it to you now, this a really incredible mission, getting OSIRIS-REx to Bennu, all the research we've done already. I wonder if you could speak, though, a bit about this process now of getting the sample back to Earth. What's going to happen? What is the process for you as researchers to get your hands on sample material, and how does it go down the line of who gets this material to work on, and what key objectives get addressed first, basically, I guess is my question.
So on May 10th, the spacecraft did a departure burn to leave the proximity of Bennu and begin its long journey back to Earth. It takes a long time because it's a low energy trajectory, so we've got to obey gravitational forces and orbit the sun twice to make it to Earth. 4 hours before the spacecraft would come to Earth, it ejects the sample return canister. That's the about this big, quite huggable device, as Scott likes to describe it, that holds the sample, and then that spins to keep it in a straight path, descends into the atmosphere. At the same time, the spacecraft does a divert burn to leave Earth, and so it can be used for whatever NASA chooses to use it for. The sample return capsule employs a drogue chute and a parachute and lands in the Utah Test and Training Range outside Salt Lake City on September 24th, 2023, a little bit before 9 in the morning. The location is mostly dependent on the winds and weather of that day because the orbital mechanics are so well understood. It's really remarkable. The sample canister, the SRC is picked up, put under nitrogen purge, and the sample return canister is partly disassembled in Utah, removing the batteries and the pyros, things of that sort, and all transported to Eve's building at Johnson Space Center in Houston, where the very next day it's opened up and the curators begin cataloging the material that's present, weighing it so we actually know how much we really got, pulling apart material for our Japanese and Canadian partners so that they get their sample. And the sample team will begin their analysis to test our over 50 different hypotheses about the origin of the solar system, all the way up to what the spacecraft did to Bennu and vice versa. To prepare for this, we will be doing rehearsals starting next summer to make sure that all of our laboratories are in tip-top shape, and that we have executed all of our data sharing and sample sharing from lab to lab to make sure that we work out all the kinks before the precious sample from Bennu comes, so that we're 100% ready.
That's awesome. I know in a video produced by NASA Astrobiology last year, you said that 60 grams, which is roughly the amount of sample we're bringing back, that 60 grams is a bounty of a sample. Could you speak to why you said that?
So, well, first of all, 60 grams is a requirement. You should remember the sample collection device when we did the tag in October was literally overflowing with material. So much so that we couldn't actually weigh it in space in our spin maneuver that we had planned. So there's no way to know exactly how much we have. It's well more than 60 grams, but less than 2 kilograms because we saw stuff leaking out. So we won't really know until we get back to Earth. But as Scott described, you can dissect atom by atom and get a lot of information from a single tiny grain. And that gives you information about that one grain. But there's a diversity of materials. There's at least 2 lithologies we've detected from our spectrometers on Bennu. In addition, the more material you have, the more subtle tests you can do. You can look for remarkably rare species and get even more information than you can with big ones. So, like, I'm interested in amino acids, just like Eve is, but we can look for the really rare amino acids, observe the chirality, observe the isotopic ratios of each different compound, and look at the precursors. So more sample means more analyses. But the most, I know I'm talking too much, but this is the part that excites me the absolute most, is that 75% of the sample or so is archived for the future. And so once we have this catalog, it'll be released and people can propose to look at that sample. So members of your audience or their children or grandchildren or people not yet born can request samples to analyze them with instruments not yet invented to ask questions we don't know how to phrase now. So sample return, just like Apollo and all of these other things, are the gift that keeps on giving for literally generations.
I love that part too. And actually, Eve, I wonder if you could speak to that for us for a moment as well. I know that you joined the OSIRIS-REx team fairly recently. And I think sometimes, some of our younger members, maybe undergraduate students, are unaware what it's like to be a scientist, to have a chance to join these teams. And you don't actually have to be there at the very beginning. You can kind of join at certain periods. And then you can also look to the future, like Jason just mentioned, with future generations working on these samples. I wonder if you could speak to what it's like to be a researcher who's now joining OSIRIS-REx and looking forward to those samples and what kinds of work you see down the road as well.
Sure. So I will say just being given the opportunity to join the team as a collaborator is just so exciting. I'm really excited. I was at University of Arizona when we were writing the proposal. So, 10 years later to be a part of it is just amazing. It's also really overwhelming because the wealth of data that has come out of the mission so far is incredible. So trying to catch up and sort of be on top of where things are, I'm still working on that part of it. But I'm just going to add something to what Jason said. It really is very small. Like if you look for something specific, if you find a mineral that tells you something, you don't need a lot of it to give you an answer. So I wrote my dissertation based mainly on a 200 nanometer grain that VILD2 returned that had some really cool properties, where it changes form at a particular temperature and doesn't go back. And it tells us something about aqueous alteration. And so I was able to write an entire dissertation positing what I thought might have happened to that grain in the history of its life, from start to finish, across millions of years. And to be able to do that from a tiny grain is amazing. And people often ask me, well, what if you're wrong? And I say, that's great. If somebody goes back, if something that I do on an OREX sample inspires someone 10 years from now to say, yeah, Eve, that was a really nice idea, but I'm not entirely sure because today we can measure X, Y, and Z that you couldn't measure. And they go back and look at the same sample or something similar. That just forwards the research. I mean, that's what science is all about, making hypotheses about science and the history of our universe based on the available information that you have. And so seeing that move forward and these samples coming back to be able to measure amino acid abundances, and Jason mentioned chirality a minute ago. So for folks who are watching that maybe aren't familiar with that term, chiral molecules are ones that are mirror images of one another. So sort of like your hands, your left and right hands, mirror image, but no matter what you do, you can't superimpose them on one another identically. And so meteorites deliver amino acids in both right-handed and left-handed forms. In fact, most of the meteorites come back and we see racemic mixtures, which means equal amounts of right and left-handedness. But life only uses left-handed. So going back to my research, that's sort of what inspires me. How did we go from equal amounts to just this one in life? And so these worry about contamination, right? Because we have amino acids on Earth, but these samples, we don't have to worry about that. So really just, again, ground truth data point for us.
That's awesome. And there's so much about characterizing life and understanding what life is as we know it and as it might be elsewhere. And so those are really important things, I think, for us to talk about. I have so many more questions, but I've realized that I also want to get to our audience questions. We have a bunch pouring in right now. And for those watching, please remember to ask your questions in the chat on SegaNet or on Facebook on the NASA Astrobiology Facebook page. We'll try our best to get through as many as we can, but I see there's a bunch pouring in already. I'd like to ask at least one more question of my own for each of you, and then I'll try to get into the audience questions. Scott, starting off with you, to change things a little bit from OSIRIS-REx, you've done a lot of work in your career, not just in sample return and in studying things like in the interstellar medium, but also in meteoritics. And I understand that you've traveled to Antarctica and have collected a large number of meteorites. And I read in your bio that you collected the Allen Hills meteorite at ALH 84001. I'm wondering if you could just speak to us about how what the experience of being in Antarctica and picking up those rocks, and let alone one of the most interesting ones of all time.
Let me begin by just correcting one thing. With very few exceptions, I never say I found a meteorite because there's a team down there and we work together. You have to work together just to survive, much less find meteorites. And so I was on the team that found the Martian meteorite. There is one meteorite I say I found because I had to fight the rest of the team to bring it back, and that was actually ended up being a large sample of the moon. But anyways, yeah, I've been fortunate to go down 3 times. There's a program called ANSMET, Antarctic Search for Meteorites, which NASA is one of the partners on, and they try to send a team down to Antarctica every austral summer. that then goes into a remote field site. They live in tents for roughly 6 weeks or so, and search bare ice patches for meteorites. And I won't go into all the details, but there are a number of reasons why Antarctica is a really good place to find meteorites. They're frozen in, so they last a long time. You don't have to be very bright to recognize a black rock on blue ice. So training is minimalistic. So the biggest problem is just the logistics of getting in and surviving. And this program has brought back, literally thousands of meteorites to the scientific community, and these are curated in much the same way the OSIRIS-REx samples will be curated. That they're cataloged, and a certain amount of minimal work is done to make sure we understand what kind of a meteorite it is, and then they're posted as available for people to request and study. So they become a resource for the entire world's scientific community. So when you go down on the Antarctic expeditions, it's kind of an adventure, and you find the meteorites. You don't do much of the science, other than some science associated with trying to figure out why the meteorites ended up where you found them. But they become available to everyone else. So it's a really important community service that gets done most years and provides us with an enormous scientific resource.
Yeah, that's incredible. I know like a large number of our meteorites have come from ANSMET, and I'd love to go down sometime. I think it sounds really cool to be involved in these missions to collect so many samples.
I would go again in a shot if I had an opportunity. It's a lot of fun. It's hard work too. They're very long days, and you're never warm, but it's pretty cool.
That's awesome. I love that so much. You're making me super jealous. I do want to ask Jason as well. Outside of OSIRIS-REx, you've done a lot of work on organic chemistry, kind of the inventory of organic molecules that could be important for origins, for the origin of life, for things here on Earth. I wonder if you could speak to our audience about the importance of understanding cometary and asteroidal materials when it comes to origins.
Yeah, so I actually started out my research career studying traditional origins of life chemistry, prebiotic early Earth simulations. And then I actually was a postdoc for Scott at Ames, where we were studying ices, and that was a further restriction of the phase space. Instead of studying things based on the models we have of the early Earth, which are not very well constrained, they're based on the models we have of the interstellar medium, which are constrained by telescopic observations. Then I had the opportunity to get hired at Goddard and start a laboratory studying meteorites. Which are even more constrained because these are actually samples that were in space and you can look at close up. And then, of course, OSIRIS-REx is the natural extension of that from a specific asteroid. And so my strategy is to look for compounds of interest to prebiotic chemistry, like amino acids, cyanide, amines, things of that sort. But what I'd like to do is, instead of doing an inventory of every single amino acid we can get in a meteorite, I like to focus on a suite of them and look at them across different kinds of meteorites to understand, instead of just making a menu, trying to understand the cosmochemistry of that was happening that could have influenced the origin of life on Earth or Mars, Europa, Enceladus, your favorite object.
That's awesome. Yeah. I think a lot of us in the audience as well have their own favorite objects throughout the solar system to talk about for astrobiology. So I'm glad you mentioned that. Eve, if I may, also kind of outside of OSIRIS-REx, you've done a lot of work in instrumentation and understanding, these sources, the evolution and changes in amino acids, but you've done a lot in kind of modeling these impact processes and how they affect organics, specifically amino acids. And that's also relevant for life. I'm wondering for our audience, if you could just give kind of your vision of the importance of understanding impact processes for the origins and evolution of life on Earth and maybe even elsewhere.
Sure. So the hypothesis that we were working with was, we know that there are amino acids in meteorites and in asteroids, and they're being delivered to multiple planetary bodies, not just Earth. And we also know that there has to be an energy source in order to give them what they need to polymerize. So we go from amino acid to peptide to protein to DNA and RNA, which eventually leads to life. And I really am really interested in that part of astrobiology too, although I'm definitely an amateur. I just watch that happen. But there haven't been a lot of experiments done looking at systematically across different sizes of amino acids or different handedness of amino acids. So we were trying to fill that gap. And we've been a little bit derailed by the pandemic, but I do have some samples that we've run but haven't analyzed yet using mass spectrometry. And when we get back in the lab, hopefully soon, we'll be doing impacts. And at Johnson Space Center, we have an experimental impact lab that allows us to simulate a specific shock pressure. So that's a flat plate accelerator. And then we also have two impact apparatuses that simulate a more open. So instead of having our sample encased inside of stainless steel, it's a more open container, so it's more natural. So our impactor hits, and we have ejecta coming out, and we have a range of pressures over which those organics that we've put into our starting material are exposed, and then we take those and we look and see what we've gotten, and compare it to what we started with. And so I guess for me, I've always enjoyed looking at a sample, a meteoritic sample or something brought back by OSIRIS or from Build 2, and then also trying to simulate that in the lab. So doing experiments. And then also sort of the third leg of that is looking theoretically and trying to put that all together, because I think we need all of those pieces in order to let us know how life started on Earth. And if we can untangle what happened here using processes that happen elsewhere, we might be able to better predict where we would find life somewhere else. Like, what are the necessary components, not just starting materials, but energy sources as well? I hope that answered your question.
Absolutely, that was great, and thanks for talking about all these different pieces. Astrobiology, is a large field of people coming together from different disciplines and bringing all of these different pieces together to try to understand our origins and what life in the cosmos really is. I really love that a lot. I do apologize to our audience. I'm going to start audience questions here very soon, I promise. First off, we do want to announce our Twitter poll. This is the very first time where we polled the audience on Twitter a question about the mission or the topic, and most people got it wrong. So our question on Twitter from NASA Astrobiology, or at NASA Astrobio, was, now that OSIRIS-REx is heading home, how far does the spacecraft itself have to travel to get back to Earth? And so we had the potential answers were 45 million miles, 110 million miles, or 1.4 billion miles. And it was actually the largest of those three, 1.4 billion miles. The spacecraft has to go around the sun twice on its way back home by 2023. It has quite a long journey ahead of it. But many congratulations to those who got it right. But there is a lot ahead yet for this spacecraft, for those samples to come back, as Jason mentioned, landing in Utah in 2023. So now I think we will jump to the audience questions. And the first question I actually already knew because it came in before the show started. And I know that Jason has an exact answer for it because we talked about it before the episode started. The first question comes from Rudy Von Reep on Facebook. Rudy asks, where is OSIRIS-REx now?
Right now, OSIRIS-REx has departed Bennu. It is 202,000 kilometers from Bennu, and it is the other side of the solar system from the Earth. So it's basically in Earth's orbit. It is 0.9 AU from the Sun and 1.9 AU from Earth. So that gives you a one-way light time of 15.885 minutes.
Lovely. Yeah, it's great to have the data. We can actually say exactly where it's at right now because we do track these things. And as you mentioned, we'll be tracking this into the distant future as well. For future generations, they'll be tracking Bennu and other asteroids in our solar system.
And if you can jump in, you can look at NASA Eyes. It's a website where the Deep Space Network updates in real time where all these spacecraft are. So if you don't believe me, you can look for yourself and find out.
Awesome. That's a great idea. I've used that website myself many times to see where various spacecraft on their way to Mars and other worlds are at and what's going on with them currently. It's a great site. Our next question comes from Twitter, from Jorge Cristobal. Jorge wants to know, could there potentially be a dangerous microorganism within this sample coming back from Bennu? And how do we control for a potential biohazard? And I'll open that up to any of you who'd like to potentially answer that question.
I'll start. I'll just my short answer to that is we have tons of material falling onto the Earth every year, meteorites landing on everywhere, and interplanetary dust particles. Scott or Jason might have a better accurate number on how much, but so we have been exposed to asteroidal materials our entire lives.
Yeah, there are a variety of estimates, but I think it's something like 12 tons a day falls in, even just as the smaller grains. So we're exposed to this stuff all the time. There's some in the room with you right now. The small dust grains, like the ones we collected at Vilt 2, slow down in the upper atmosphere and take anywhere from a couple of days to a couple of weeks to settle out to the ground, and then they just get down on the ground and mix with all the cat hair and dandruff and everything else. So you've probably got some comet dust in your hair right now. It's quite possible. So for these particular kinds of materials, there's no real biohazard. In fact, since this has been going on for the entire life of the Earth, maybe it's good for us.
So I can expand on that even further. So in the case of Bennu, it's a very small asteroid, only 500 yards across, which means that it though we have evidence of water, it's not liquid water. It's not flowing water. So there's no environment for life to form. It's been irradiated by galactic cosmic rays for eons. So any life that could have formed, which it couldn't have, would have been sterilized. The surface is very hot. So anything that could have formed but couldn't have, would have been sterilized, would have been killed. And furthermore, we now know that Bennu is ejecting rocks all the time. Centimeter-size pebbles are coming off of Bennu. Bennu does cross Earth's orbit, so we would expect there to be a Bennu meteor shower every September in the southern hemisphere. And so those generic asteroid rocks that hit the Earth, actually, some of them are coming from Bennu. We just have no way of identifying them, hopefully, until we get the sample.
I mean, it's entirely possible we have a sample of Bennu in that inventory from Antarctica. We just don't know it. But when we get the Bennu sample back, we'll be able to compare against the rest of the data set and do some detail, and maybe we'll find out that we can prove that this has happened.
Yeah, that's a really good point. I think a lot of folks, we have Mars meteorites that we can show came from Mars because of the atmospheric analyses we've done on Mars, but we certainly have meteorites from other bodies in our solar system that we just can't pair them up. So that's one thing with sample return too. We actually then can do the inventory and actually compare those to other data. That's a really, really good point, I think, for our audience.
True. It's also possible that the rocks from Bennu are so crumbly, as we saw from the TAG event. The TAG arm sank into Bennu by perhaps half a meter, that maybe the rocks are so crumbly that they don't survive long on Earth, that they don't pass through the atmosphere without breaking up into dust. And if they land on the Earth, maybe they dissolve within days or hours. And so they may be on Earth and we just never have seen them.
And you just mentioned that the TAG event. We have another question from Anirudh Mohanty, one of our ambassadors of the month, who asks, so the Mars parachutes were tested in wind tunnels at NASA Wallops and NASA Ames. He wants to know if and where the OSIRIS-REx boop was tested. Where was the TAG process tested anywhere? And what was that test like?
It was tested so much. It was the technology developed by our partners at Lockheed Martin Space Systems, and they tested it in under vacuum chambers on Earth with a whole range of materials and range of orientations. They tested it on the Vomit comet, the parabolic airplane, to check it under microgravity. It was difficult to do under full vacuum and microgravity at the same time, but they did extrapolations. So it's been tested an enormous amount under various different designs to then optimize it. For example, we optimize the amount of gas flow, because more gas means more pressure gas means more sample. But we also discovered that you can also pop up off the surface if there's too much gas, acts like a thruster. And so we had to tailor that based on the dynamics of the spacecraft touching the asteroid, based on our understanding of the asteroid before launch, which changed somewhat when we got there. So it's been tested an enormous amount. We also tested the parachutes, of course, by dropping things from helicopters.
Yeah, I'd point out that the sample return capsule for OSIRIS-REx is based on the Stardust capsule. And so it also got lots of testing. It was dropped in the desert and before. So there was already a data set available for OSIRIS-REx to begin from.
Indeed.
I would just add that the TAG-SAM is one of my favorite parts of this mission. And a few years ago, as part of my job, I was able to work with a program with engineers. So partly getting engineers and scientists to learn how to work together, but they were designing sample return missions using little helicopters. And they had to actually design a way and successfully pick up samples from a Mars yard at Johnson Space Center. And so working with them and finding ways not only to collect successfully, but collect cleanly, making sure that you're not adding anything to the sample. And so TAG-SAM to me is just an engineering marvel, and it's amazing.
Yeah, I think everyone loves it too. Like the idea that there's this cosmic boop, right? I think everyone really loved that. Scott, I'd like to direct the next question to you. This comes from Jim Pass. He's at Astrosociology on Twitter. Jim wants to know, what can analyzing this sample from Bennu, and really what does this work reveal to us as a society that really benefits the future of humanity?
Well, I think I'll go back to yet again to Jason describing our acronym. There's actually not one answer to this. Let's just pick a really big scale one. Since Bennu is in fact one of the larger potential hazards for an impact with the Earth, if it did that, the destructive nature of that event would be pretty serious. And so our understanding this object and understanding the dynamics of such objects and being able to understand the material from which this object was made, how that might affect how you could manipulate it, could play a major role in literally saving millions of people in the future. So there's a big scale one. I'm a scientist, so at some point maybe I put more emphasis on this than maybe your average person does. But the solar system is our neighborhood, and I like to understand our neighborhood. And so just the raw science, the raw understanding of what's going on around us, I think enriches our lives, enriches our understanding of the universe we live in. And so I personally see that as a big value as well. And there are others, but maybe I'll shut up and let one of the other two weigh in on this.
Go ahead, Jason.
So let me first clarify. Scott has said, if I want to make sure it's stuck in everyone's mind, the potential for Bennu impact is in over 150 years. So there's lots and lots of time to worry about that. There are many more present dangers you can focus on rather than worrying about this asteroid impact. And it's not it would be a local catastrophe, but we have enough information to prevent it. So that's great. We also have learned how to navigate around a small object, something this small that has microgravity. So that will be useful for, say, future asteroid mining, future exploration of the solar system, either robotically or with humans. And of course, we're all here for astrobiology, and that's my favorite part, is the origins aspect.
I would agree that the origins aspect is also my favorite part, but one of the things that I hope comes from the mission is that future engineers and future scientists are so inspired by what they saw and all of the records that OSIRIS-REx has met and exceeded on its own, that it gets their imaginations going and they start planning, missions for the future. And so I think even without all the scientific data that we're going to get, which is going to be fantastic, the things we're going to learn, I think we're also going to promote future scientists and engineers. I already said that, but that's sort of what I think, a big picture beyond the mission effect.
I love that so much. I know we have students watching this show who might be interested in being those future scientists and engineers who are taking part in that. And actually, there's another question kind of along that line that I'd like to start off with you, Eve. Aaron Francis on Facebook wants to know if there are any emerging techniques or technologies that you're most excited about being applied to Bennu or potentially being applied to these samples from Bennu.
Oh, gosh. That's a really great question, and I'm so stuck in my own little world these days. But what I will say is, I know that for liquid chromatography, mass spectrometry, new capabilities are being developed by companies every day. One of the companies just came out with a new way or a new material to build things with, so that more of the material goes through the system and gets analyzed. So things like that are happening. I know transmission electron microscopes are getting more and more accurate and can measure to higher and higher degrees. So all of those little changes will add up. I apologize that I don't have a specific, really big one right now, but I will say just you see small incremental changes in the instrumentation over time are amazing.
Yeah, I'd add that, we're going to be studying these samples using techniques that probably didn't exist when OSIRIS-REx launched. When we flew Stardust, I and got back and did the initial analysis of the samples. I went and looked at all the techniques we used and then compared it to the list of techniques we told NASA we would try to use on the samples when they came back. And the overlap wasn't all that big, actually. Techniques had developed so much over the course of the flight of the mission that we were doing things to the samples that we hadn't even imagined when we first started. And there's no reason to believe this will stop. The fact that the samples go to a curatorial facility where they'll be available for decades to come just means that will just keep happening.
And to combine those two answers, when we first wrote the proposal for OSIRIS-REx, we hadn't included ultra-high resolution mass spectrometry, which is one of the techniques that's being applied to liquid chromatography and other techniques, which had existed but was really out of the reach of these sorts of samples, and now they are almost routine, and they will shed tremendous amounts of information. And our sample analysis plan now includes several different approaches with different kinds of ultra high resolution mass spectrometry.
Yeah, there's too much ahead, and it is hard to predict the future. Who knows what the great techniques of the future will be? But yeah, we're very much in that kind of that realm of pushing this fringe and learning and using new things. It's like the Galileo spacecraft used a much different camera system than we would have sent by the time it actually got to the Jovian system. And these things happen in space exploration. So I'm very glad you pointed that out, Scott. Our next question comes from Tom Caruso on Facebook. Tom has been watching the show for quite some time, and I happen to know that Tom loves the icy ocean worlds of our solar system. And so his question isn't too surprising to me. He does thank all three of you for your time, and then he wants to know if you can describe what we've learned so far from Bennu and whether that will possibly tell us anything about the rocky cores of these ocean worlds in our solar system.
That's a really great question. I'm going to be the first to say that is so far outside of the realm of my expertise that I would be making something up to answer it.
I don't know much about the cores of these objects myself, but we do, I think, believe that objects like Bennu are quite primitive in the sense that they've been altered since they first formed, but they haven't been altered to the extent, for example, the Earth or these kinds of satellites have. And so studying objects like Bennu at least gives you a better understanding of kind of where you started from. So the cores of these satellites have really had a very specific history unique to themselves. But they were initially made from materials that spent time in the solar nebula and went through those processes. And so I don't know that Bennu can use to directly address the nature of the cores of these satellites, but it certainly gives us a hint of the kinds of things that would have been in the ingredients list for the cooking. That's a very different recipe to make one of these satellites than to make Bennu, or the Earth. But at least some of the ingredients may have been similar.
Indeed. The other thing, you're both correct. It's very hard to say something specific. We look at the samples we have learned more about perhaps how impacts form on very loose rocks that might perhaps melt into cores, and that maybe that helps, maybe it doesn't. But we also have learned that we have evidence of rocks on the surface of Bennu from perhaps Vesta. And so that tells us something about how these bodies can exchange material, which is something that hadn't really been thought about so much. And so perhaps we'll get a piece of this Vestoid back. And if Vesta, then maybe Ceres too.
Now, that's incredible to think about. I think a lot of people are kind of unaware that in the very early solar system, there were so many worldlets just flying around and crashing into each other. And that's how we get things like Vesta and Ceres and some of these other bodies we see now. It wasn't all just formed the way it is now. There's a lot of change in the early solar system. So that makes me wonder a lot about the samples we might get back now. And if there is some Vestoid material, and I love that term too, Jason.
So we know from returned meteorites, many meteorites are breccias. They actually are ensembles of rocks that really have very different histories that got together on a parent body and then ultimately made it to us. And so it's quite clear these objects do, in fact, swap materials back and forth and definitely did it and probably did it at a very high rate in the early solar nebula.
We've even observed enormous breccias on Bennu, meters across breccias. So the breccias we now know are both fine scale in the micron across all the way up to meter size breccias. So this tells us something about how planetesimals form, and I'm sure someone smarter than me could apply that to the cores of ocean worlds.
Love it. Yeah, again, astrobiology and planetary science, we are these large fields bringing together all these different studies so that the work you're doing right now in organic chemistry and in understanding these materials forming on Bennu and in the samples we're returning can teach us about these other worlds, the expertise of other scientists as well. And I really love that. Our next question comes from Sanjoy Sam using SegaNet, but I want to alter his question just a little bit. He wants to know what all of your favorite solar system objects are. I'd like to alter that just a little bit and say, if funding wasn't an issue and you could choose whichever mission you want to create to go to some solar system body, what would be the mission or the body and why?
I can't narrow it down to one object. I mean, professionally, my interest is in small primitive bodies, so asteroids and comets. I have to say, I do have a sort of special soft spot for Jupiter's moon Io. Back in my postdoc days, I actually got telescopic data of Io that allowed us to identify the molecule SO2 on the surface and figure out that many of the ices on Io must be large, giant sort of like ice cube type things as opposed to just frosts. So that's a pretty cool object, but that's a pretty far stretch from astrobiology. So it's more of a personal favorite than a scientific favorite.
So my favorite object is Earth because that's where we know that there's life, and that's where my house is and where I keep my stuff. But if I had to get a sample from somewhere, I'd choose Arrokoth, if that's how you say it. That is a truly primitive object that's never melted. This is the thing discovered by New Horizons. It's out past Pluto. And having a sample of that back on Earth would be just amazing and a technological miracle. We don't have that ability right now. But, if I had my fantasy, it would be a piece of that.
I love it.
So, like Jason, I am fond of the Earth. I also have a fondness for Titan, but if money were not an object and I had the engineering skills, like Scott, I am a sucker for the primitive material, so I really want comets and asteroids. So if I could send something out, sample stow, and have it hop from asteroid to asteroid, and maybe pick up a little bit of comet tail and a little of coma material as it flies through, then why not? That's where my money would go.
See that, audience? Those paying attention. The primitive asteroid hopper is the mission you need to build for Eve for her future research.
Yeah, well, if we're thinking about future missions, I also second Jason's thing about ice. I mean, when I'm not doing sample return missions, my laboratory work is largely trying to understand the molecular formation of molecular complexity from processing ices. And there are a lot of ices out there, not only in the outer solar system, but also in the dense molecular cloud from which our solar system formed. And so getting a sample of ice would be great. That's technologically a real challenge, but you did say money was no object, so I think it's fair game.
Indeed.
Well, let's get ourselves a couple meter core for stratigraphy too.
Sure, why not?
I think I want to ask one more question before we wrap the episode here. This one comes from Kashish Gupta. She's on Facebook today. And Kosh wants to know, as astrobiologists, not just for OSIRIS-REx and studying those samples, but in general in your research, what is your favorite piece of equipment, instrument, or laboratory technique? And at what stage of your career did you really get into that technique or that instrument?
I can start on this one if you like. So I really love the transmission electron microscope, but I love it in conjunction with liquid chromatography and mass spectrometry, because if I take my sample and I extract my organic materials, I can find out all the details about the amino acids and other organics that are in there. And then I can take the residual rock, I can prep it for transmission electron microscopy, and I can tell you about the rock those amino acids might have been associated with. I can tell you about its mineralogy and the interconnectedness of the minerals. But really, as much as I love instrumentation, anything that allows me to get my hands dirty in a lab is always going to trump analytical. I love mixing together, cometary simulant, or making fake asteroid for impacts, or simulating, tidal pool evaporation and recondensation on the Earth in a tiny little reactor. Those are the things that I enjoy the most, but taken as a whole. And I think the other part was, when did I start doing that in my career? Early on. So really as an undergraduate, when I was doing my degree in chemistry, I started doing experimental work and also looking at extraterrestrial samples. And I sort of made that a focus for myself as I went on for schooling and in jobs, to make sure that I was choosing careers and places that would allow me to exploit all of my interests simultaneously.
Groovy. Scott or Jason, do either of you have a favorite technique?
Well, I don't have any technique that will let me figure out things I'm trying to figure out is a good one for me. I have a real fascination with these isotopes and what they can tell us. But I guess if I had one technique that's been with me the longest, would be infrared spectroscopy. I did my thesis work taking the infrared spectra of comet dust and asteroid dust collected in the upper stratosphere using the high-altitude U-2 aircraft that NASA was flying and collecting. And then also took IR spectra of meteorites. And then when I came to work at Ames, I flew on the Kuiper Airborne Observatory and took telescopic data of objects throughout the universe in the infrared. And then use that to compare against samples that I make in the astrochemistry laboratory, where I take ices and irradiate them and break down molecules, make new ones. And infrared spectroscopy is at least one of the techniques we can use while we're looking at the ices in situ. So it's been a real workhorse, and particularly for someone like me who's interested in understanding how these materials take their history back into the interstellar medium. We're never going to go to a dense molecular cloud, at least not until someone invents a warp drive. We're not going to go to a dense molecular cloud and get samples. So simulation is kind of the only way to go, and the only way we can know what to simulate, what the ingredients in the recipe are, is to take remote sensing with telescopes. And infrared spectroscopy is very powerful for measuring molecular bonds at a distance.
Yeah, and my answer is, I'm afraid, similar to Eve's. I started using liquid chromatography when I was a high school intern, so it's been a very long time. And coupling that with mass spectrometry, which I believe that our lab at Goddard is the first one to use liquid chromatography, mass spectrometry to study meteoritic amino acids. And so that work pioneered has led on to new things. But I'll also say that as great as it is to take this technique to pull apart complex mixtures, it's also really sad because it comes at the expense of destroying the sample. And so I'm hoping that someone can come up with a way to look at the sample in situ as a rock and pull apart all the individual compounds in the mixture without having to destroy the rock as well. But that technology doesn't really exist yet, for at least the kind of information I want.
So there you go again, viewers. There's another future way that you can be involved and change the future of this research. Drs. Berger, Sandford, and Dworkin, thank you so much for joining us today for Ask an Astrobiologist. It's been a true pleasure having you on.
It's been fun.
Thank you.
Thank you.
And for all of our viewers who are watching, maybe for your own entertainment, go on Twitter, use the hashtag AskAstrobio, tag @Sagan.org or tag @NASA Astrobio, And just let us know where you would want to collect samples from in our solar system to bring back to Earth to study. And if any of you want to know more about the OSIRIS-REx mission, what's been done so far, and what lies ahead for the future, you can go to asteroidmission.org to find out a whole bunch more about the team, the mission, the science, and lots more about OSIRIS-REx. And for those who want to stay in the loop for upcoming episodes of Ask an Astrobiologist, or get more information about opportunities and news in astrobiology, you can sign up right now for the NASA Astrobiology newsletter that goes out through email and announces big things like our show, like when we have a tag event and other cool things going on in astrobiology for all of you to stay up to par with what's going on in this realm of learning about life in the cosmos. So a huge thanks again to our panel for joining us. Thanks to everyone for watching. And as always, remember to stay curious.